Welcome, everyone, and thank you for joining us today. My name is Kara, and I'm with the LTAP Center here at ODOT, and I'll be your host for this webinar. Today's webinar is Barrier Inlet Screens to Mitigate Debris in ODOT Storm Sewers, and we're thrilled to have Justin Kearns, Troy Lyons, and Andrew Turpick as our presenters. Before we begin, I'd like to cover a few housekeeping items to ensure a smooth webinar experience for everyone. If you have any questions during the presentation, please use the questions panel on your screen. You can type your questions there and they will be addressed during the Q&A session at the end. If you're experiencing any technical difficulties or have any other issues, feel free to use the chat panel to communicate with our team and we'll do our best to assist you. Please note that this webinar is being recorded and the recording will be made available to all registered attendees after the session. All right, with that out of the way, let's get started. It's my pleasure to hand it over to Justin Kearns. Justin, the virtual floor is yours.
Thank you. And thank you all for joining us this morning. We look forward to sharing our results from the Barrier Inlet Screens to Mitigate Debris in ODOT Storm Sewers research project. I'd start by introducing the team. MS Consultants served as the principal investigator for the research project. The Ohio State University, Ryan Winston and Andrew Turpick served as co-principal investigator and led the field monitoring and debris analysis portion. University of Iowa, Troy Lyons, Marion, and Tony Lozier also served as co-principal investigator in charge of laboratory testing and physical modeling. And then also want to take a moment to thank the ODOT Technical Advisory Committee for all their help and assistance throughout the project and this opportunity to perform this research. A little bit of background about this project. As we all know from driving around on roadways ourselves, roadways can be a source of trash and debris and other pollutants. Everything from fine soil particles, grass clippings, leaves, and hubcaps inevitably ends up on the roadways. And when it rains, this gets washed into the drainage features and the roadway inlets. This research project focused primarily on barrier inlets due to their susceptibility to this debris issue. Now, the barrier inlet you all are probably very aware of, whether you've noticed it or not, along the highways are the concrete barriers that divide traffic. And in the ODOT world, these barrier inlets are comprised of a very short but long inlet window, as you see in these pictures, 4 inches tall by 10 inches wide. And due to this particular geometry, large debris like plywood, buckets, anything that you're looking to fall off a car or can be found on a roadway can get swept into these inlets. And once it gets into that very small opening, it's very difficult to get out. So ODOT maintenance crews have to perform very invasive sewer cleaning and other maintenance practices in order to clean out the inlets after debris has gotten into the underground storm sewer system. And of course, this poses a risk to the roadside maintenance crews who are exposed to traffic for extended durations of time. This picture here, I think, shows a good example of the kind of issue we're dealing with along the roadways. As you can see in this picture that was taken down in District 8, which is near Cincinnati, a small piece of plywood, about 30 inches long, 12 inches tall. That's the type of geometry of this debris that can be swept into this inlet. And once that piece of plywood got into the underground storm sewer, it oriented itself just so that it was able to block the outflowing pipe underground. And it led to this large debris backup and backed up the whole system. As you can see in that picture there on the right, quite a bit of debris was unable then to leave the sewer system, and this had to be vacuumed out and creates a big maintenance issue for ODOT maintenance crews. And if left unattended, this can obviously cause the inlets to clog and have reduced hydraulic efficiency. So the goals and objectives of this project is to prevent the large roadway debris from entering these systems. The large debris is what we find is causing these underground sewer clogging issues and are the most difficult pieces of debris to remove once they enter the inlet. So we really focus on the large debris. We conducted this through a combination of laboratory and field testing of various inlet screen devices. And then we identified our optimal solution as one that could balance safety, hydraulic performance, operation and maintenance costs, and obviously provide water quality benefits to the downstream receiving waters. This research kicked off in September of 2021 with an extensive literature review and a review of all available products that are currently on the market to address this particular problem. We then developed our testing methodology, installed field monitoring sites, constructed a physical hydraulic model setup at the University of Iowa, and did all of our testing for about 2 years. And that brings us here today, giving this final presentation, and we'll be wrapping up our final report in June. So like I mentioned, we started with a very extensive research of all the available products on the market to identify what current solutions are out there that we could test. And we identified a large number of proprietary manufactured products. And then using a selection matrix that evaluated different factors and different product features, we were able to identify 4 products that contained a good cross-section of the market. We wanted to test different attachment mechanisms, different opening geometries, different special features. Some of these screens are automatically retractable, so they have springs that are able to adjust. The bars can kind of open up when there's heavy hydraulic loading. So different features, and just wanted to test a variety of characteristics to see which performed the best and would provide the best benefit to ODOT for their particular needs. In addition to the proprietary screens, we also fabricated some of our own unique designs. Because ODOT wants to focus on the large debris, the debris that's really causing them their issues is on the larger side. So we created some inlets screens that had bigger openings than what is typically available in a commercial product. And because of the application of these along existing roadways, there's quite a bit of geometry deviation in these inlet windows across the roadways. So we wanted a product that could be easily bolted to the face of an inlet and could be more forgiving in terms of geometry that could be applicable and be a better suit maybe to a statewide kind of mass scale implementation. So this picture here shows one of our screens and how it is TAPCon to the barrier inlet screen. Like I said, we designed it to cover the whole 4-inch tall opening, and then we had one variation that was a little shorter. We wanted to test what would happen if we left a small gap at the bottom and small gap at the top to allow maybe smaller debris to pass under the screen and provide the emergency overflow over the top. So between the manufactured screens and our own fabricated screens, we identified just a whole different variety of opening sizes and characteristics to test in terms of debris capture efficiency as well as hydraulic efficiency. This is the standard ODOT Type D number 3 single slope barrier inlet. This is the most common one that you will see along ODOT roadways. So this is the one that we focused our design on, and it includes the inlet window, which is 10 feet wide and 4 inches tall. And they are outfitted in front there. You see that catch basin, which is a Nina slotted grate, 30 inches by 36 inch geometry. Worth noting that the grate, the catch basin grate, in some installations it is there in front of the inlet, but the inlet window can also stand on its own without that slotted catch basin grate. So we tested both of those potential scenarios in our testing. So now I'll turn it over to Troy Lyons to talk about the laboratory experimental design.
Yeah, thanks, Justin. So I'm going to go through the laboratory experimental design and the testing that we did in the lab to evaluate the barrier inlet performance and screens. And so the rendering that you're seeing on this slide is the test channel that was fabricated here in our lab at Iowa. The main feature is a 12-foot wide by 50-foot long channel or test deck that creates a channel for water to flow through. It represents the shoulder of a highway along with a concrete barrier inlet. and the concrete barrier itself. So the wall where the inlet's at is sloped to match the design, the standard ODOT design. This is a full-scale test channel. So we discussed doing a reduced model scale to be more cost efficient, but a couple of advantages to doing it at full scale. One is that we could purchase the existing screens directly from the proprietary groups, so that we didn't have to try to replicate something at a reduced size. And we also didn't then need to scale the debris. We could use actual debris for the debris tests. So flow is conditioned as it enters the head box. So there's a 10-foot wide by 16-foot long head box at the upstream end. So we pump water into that box. The water then flows down through the test channel. Some of the water is intercepted at the barrier inlet. The remaining water that flows past flows freely off the end of the test channel. We measure water flow rate into the head box so we can set an exact flow rate. We also measure water coming out through the barrier inlet so we can calculate what the intercepted flow rate is. The test channel can tilt longitudinally between 0 and 5 degrees, pivoting up here at the head box. It can be raised and lowered at this end. And we can also tilt it laterally or cross slope 0 to 5 degrees along the axis of the barrier inlet. And the barrier inlet's placed about 2/3 of the way down along the 50-foot channel. So this slide shows a time lapse of the fabrication of the test channel and how it was set up. So we started with 3 50-foot long steel beams to support and create a rigid 50-foot long bed. That was then elevated, set into place. You can see that happened just there. We modified an electric car hoist that was placed at near the downstream end so that we could raise and lower it. And then we had intermediate supports that we placed along the channel for our fixed positions that were required for the testing. You can see there in the background the piping from the pumps. So we have an underground reservoir that holds water, so we can pump water out of that into the head box through the channel. And then it comes out of the barrier inlet into that side channel that you can see is being fabricated there, and flows through a V-notch weir that's installed at the end of that channel so we can meter the flow coming out. And then the rest of the flow, including what's going off the end of the test deck, combines, gets filtered through some screens to filter out any debris. The water goes back into our sump, and that clear water then is recirculated back into the test channel. So we did a friction slope calibration of the test bed. So in our lab, we created the surface of the road deck out of plywood, but we knew that wouldn't provide us the correct friction slope. And so we did an evaluation using Manning's N to check it and see what it started out to be. And then we incrementally roughened it to achieve a target Manning's N to match that of concrete or asphalt. And so we did that by iteratively adding sand embedded in epoxy paint to roughen the surface, and we ended up getting a Manning's N of 0.0144, which is very close to our target of 0.015. So that way it ensures that we get the correct flow velocities and depths for a given slope combination. The equation shown here in this slide is the relationship between Manning's N, the flow rate, the cross slope, the longitudinal slope, and the width and depth of the flow. So for our test flows, we use the rational method to determine appropriate range of test flows. And we chose half-acre and 1-acre areas as representative of typical field sites. So we did some evaluation of existing sites, and those were good choices or reasonable choices. We used the Ohio IDF curves for rainfall intensity, and then we chose a range of flows that went from 2.4 CFS, which represented a 10-year return event for a half an acre area, up to 7.9 CFS, which represented a 1,000 year event for a 1 acre area to represent an extreme condition. And just to note, 7.9 CFS is about 3,500 gallons per minute. So these are two videos. The video on the left clearly shows the grate that we use. So this is a standard Neenah cast iron grate with the longitudinal slots. That was used or installed for all the tests. But then the video on the right shows that grate blinded off. And so to basically take away the effect of the grate, we just covered it with a thin piece of stainless steel sheet metal. Also point out, there's the point gauge here and the same point gauge here. There's also one upstream that's just off camera that you can't see. Those were used to measure the water depth above the screen, and then upstream and the flow approaching the inlet. The inlet here is on the left side alongside of the grate in this video. As you'll note from these videos, the hydraulic characteristics between these two are quite different. These are at the same flow rates, but in the video here with the grate open, you can see a large portion of the flow is intercepted by the grate. These initial tests were done to characterize the hydraulic performance of the barrier inlet with and without the grate. So we metered the intercepted flow and then used that to calculate the hydraulic inlet efficiency over a range of different longitudinal and cross slope combinations. And what that did was provided us baseline hydraulic characteristics to later compare for when we added the screens onto the inlets. So to determine what debris we were going to use in the lab, we had to do some type of a characterization. And so there was two sources that were quite helpful. One is that while we were designing and fabricating the test channel and then doing the initial hydraulic analysis, Ohio State was already out in the field analyzing sites, collecting debris, and so they were able to characterize what they were finding at the sites that were selected for the field observations. That helped inform what we used in the lab, as well as a study from 2019 that was done for ODOT to characterize the debris collected by street sweepers. And that's what this graph is here on the right. It's a pie chart of the debris composition by weight. The large blue area, over 80% is by weight, is sand and fines. And then after that, rubber, tires, plastics, and then to a lesser extent, glass and metal. So what we ended up using then was a mixture informed by both of those, what we were seeing in the field as well as the study that we had access to. So we ended up using 82% by weight of sand and fines. And then we used, most of the rest was large debris mixture, wood, plastic, aluminum cans. We did not use metal or glass, and we did add straw to simulate debris from mowing and then mowing debris, as that was identified as a significant risk for clogging. So we ended up with a large debris mix of about 5.5 pounds by weight, 1.1 pounds of straw, and about 30 pounds of sand that we used for each test. Here's just a photo showing an example of the large debris that we used. So some of this was debris collected from roadways, and other was just representative of typical things that could be found. So hubcap, aluminum cans, plastic bottles, pieces of rubber tire, plastic grocery bags, a bucket lid, chunks of construction lumber, a strap, and some pieces of cloth. So these are just two photos, but wanted to point out the difference here. So the difference between these two photos is on the left, the grate's open, on the right, the grate is blinded. So we observe from this test that significantly less flow is intercepted when the grate is blinded. So you can see the ponding depth is further out into the roadway. So the edge of the water is here. When we have the grate open, it really doesn't come out past the grate itself. We also see different characteristics in what happens to the debris. So in this one with the grate open, because most of the flow is leaving the test channel and not going beyond, it leaves a lot of the debris behind and a lot of it on the grate, which is where a lot of the flow is going. When the grate's blinded, we see a lot of the debris actually going past and just along with the flow going past and not staying on the grate. So here's a video showing a typical debris release. We repeated debris releases with the same debris for every test and the same method for every test so that we would have a good comparison between tests. For this particular video, the SOP technology screen is installed and the grate is blinded. You can see right there the orange strap and a plastic bag just got stuck on the screen and significantly changed the ponding and spread on the roadway. So you can see a very immediate response hydraulically to the trash and debris that's being impinged on the screen. These two images show another condition. Another condition that was identified as being important is a sag condition, where we have an inlet in a low place where water would be flowing from both directions, and the only option would be to go into the inlet and not go past it. Because we had a rigid deck and we didn't have a way to slope it in multiple directions, what we did instead is we replaced a bulkhead across the downstream end of the channel to stop the flow and basically create a pool in front of the inlet where all the flow had to exit through the inlet or the grate. And some results that you can observe here in these photos, when the grate is open, the flow depths are less, which means it's taking much more of the flow through readily without needing to build up head to drive it through. We are seeing a lot of the debris collecting on the grate. Over here where the grate's blinded off, the depth is higher, so we have a kind of a big recirculating area here. A lot of the debris stays floating, but does eventually go to the inlet itself and get impinged on the grate or go through if there's no grate. So the grate was shown to be quite beneficial in a sag condition, both in keeping the water levels down, as well as keeping being less prone to clogging. And then in terms of how we quantified the lab results, this table is an example of one table of many that are in the report, but basically showing the rows here are ordered by flow rate. So on the left here, the 2.4 CFS up to 7.9. And then the columns are ordered by decreasing hydraulic efficiency. So here on the first one, the baseline is the most hydraulically efficient. And then all the way down, we go through the 3 fabricated screens, type A, D, and C, and then the 4 proprietary screens. So this specific table is showing values for a half percent longitudinal slope, 4% cross slope in the sag condition with the grate open. And really the takeaways here were that in general were that the fabricated screens, the A, D, and C are more hydraulically efficient than the proprietary screens. And also the catch basin, whether it's blinded or open, also has a significant impact on the hydraulic capacity. And then my last slide here, before I hand it to Andrew, just a few more takeaways. This is a close-up view of the SOP technology screen, which was found to be the most hydraulically restrictive. But really, the proprietary screens were more prone to clogging because they did, in general, have much smaller openings, which means they didn't allow as much debris through. Conversely, the fabricated screens with the larger openings were more hydraulically efficient. They were less prone to clogging because they let more of the smaller to intermediate sized things through, but they kept the large debris out, which was the goal. And finally, the graded catch basin does significantly impact the ability to handle debris and to handle flows. So Andrew, it's all yours.
All right, thanks, Troy. So Ohio State was tasked with performing some field monitoring of these barrier inlet screens on actual roadways across Ohio. At the onset of the study, we consulted with the TAC to identify areas of hotspots for debris accumulation. And to no surprise, these were located in the greater Cincinnati, Columbus, and Cleveland areas. So this is ODOT's districts 12, 8, and 6. You can see there on the map. In each of these regions, we identified clusters of barrier inlets. So we had 8 barrier inlets in each of these regions. And the idea there was we wanted to try to minimize any variations between climatic factors or traffic or littering practices, if you will, and to try to basically congregate each of these screens in an area that was relatively the same in terms of treatment. So in total, we were able to test each screen in triplicate. So we had one in each of these districts. And we also had a control in each district. In other words, an inlet that did not have a barrier inlet screen installed. So we could compare the barrier inlet screens against current practices in the state. So after we identified our sites, the research team was sort of faced with an interesting challenge here in that we needed to monitor and be prepared to rapidly respond to drainage issues on the roadside in districts that were over 200 miles apart. And so to address this challenge, we turned to real-time monitoring of these inlets across the state using some internet-connected depth sensors that we built in-house at Ohio State. We also paired those sensors with wildlife cameras to provide photo documentation of the debris, and then performed sampling at these inlets when we met certain conditions, which I'll show here on the next slide. So this is sort of a schematic of our field monitoring setup. So this is an example of what was done at each of the 24 barrier inlets that we studied. You can see here, most of our equipment was installed on top of the barrier wall and sort of looking down immediately in front of the barrier inlet itself. So in each one of these inlets, we had our ultrasonic depth sensors that were connected to the internet and streaming data in real time. We also had that wildlife camera, as I mentioned, which was installed on a mounting apparatus, pointing down and allowing us to photo document debris as it became trapped in front of and sometimes moved from each barrier inlet screen. In each one of our cities, we also had a tipping bucket rain gauge near each inlet cluster, so we could monitor rainfall patterns and sort of test the effects of rainfall depth, rainfall intensity, dry periods, et cetera, on debris accumulation in front of the barrier inlet windows. And then the last piece of information to mention on this slide here is we established what we refer to as a failure threshold. So over time, we knew that these barrier inlet screens were going to have debris accumulate in front of them. And as a result, their hydraulic capacity would diminish. Because we were working along actual roadways, we wanted to make sure that we had a certain level of safety such that we weren't creating ponding conditions that extended into the travel lanes and posed safety risks to the motoring public. So the way that we determined that was the equivalent depth of water that corresponded to a ponding spread that encroached within 1 foot of the travel lanes. You can see that here in the dashed line on this figure. So once we had measurements from our depth sensors that corresponded to that ponding kind of encroaching closer to the travel lane, we went out into the field, removed the debris, and took it back to our lab for analysis. Here's just a quick schematic, an image of the inside of what these depth sensors look like. Really 2 kind of critical points to highlight here. The first is this gray bell-shaped component on the bottom of this sensor node. That's our ultrasonic depth sensor, which provided high resolution depth measurements that we could transmit over the internet via this sort of second piece here, which is this piece in the middle, which is a LTE connected development board called a particle boron. So those of you who might be familiar with an Arduino, this is a similar setup. and we are transmitting these readings over an LTE or a cellular connection in real time. And then we set up some alert protocols to alert research staff when that debris needed to be collected because we were posing safety risks potentially due to the extent of ponding in front of these screens. Here's some images of what it looked like in the field. So monitoring equipment went in April of 2022. And of course, when we were out there in typical Ohio fashion, we had a pop-up snowstorm for the first 10 minutes that we were out there. But as you can see on the picture on the right there, the weather did eventually clear up for us. And you can sort of see the orientation of both the ultrasonic depth sensor and the wildlife camera there, mounted to the barrier inlet wall and pointing down just in front of the barrier inlet itself to record photos and collect those ultrasonic depth measurements. So in addition to our ultrasonic depth sensor and camera, we also did some other kind of marking of the pavement to help us quantify the size and perhaps even the travel time of the debris stuck in front of these barrier inlet screens. So we painted this 4 foot by 12 foot grid on each of the inlets to help gauge debris movement because we knew that we might have a piece of debris that contributed to a clogging event, but then maybe was transported before we could get out into the field for collection by wind from passing vehicles, et cetera. So we wanted to really make sure that we could accurately depict what was there and what created the clogging issue in the first place. Some of our inlets had grates, as shown in this picture here, but some, in fact, half of our inlets were barrier inlet window only, so they did not have that catch basin grate. So what we did in order to make an apples to apples comparison across the 24 barrier inlets that we were studying is to use sections of silt fence to temporarily block off those grates and encourage all water to flow in through the barrier inlet windows themselves. Here's an image, a time-lapse video of kind of field monitoring in action, if you will. So this is a large rain event, 2.3 inches over the course of 2 days, about 6 weeks after we installed the barrier inlet screens. A couple of pieces of things to point out here. So first, you can really see the amount of runoff and amount of water that gets directed to these barrier inlets. And that's just a result of the fact that the drainage areas feeding these are completely impervious and are also extremely efficient in their ability to convey flows to these inlet points. The other piece that I'll point out here is this plastic tote lid that you can see stuck in front of this barrier inlet window. That is almost exactly the type of debris that we are trying to prevent from getting into the sewers, and is very similar to the piece of plywood that Justin showed earlier in the presentation that created that debris backup in District 8. So if that were to get into the sewer and orient itself perpendicular to flow, this is certainly a piece of material that could result in a huge maintenance burden to unclog sewer pipes down the road. So here's an example of rainfall data and a hydrograph from our first failure storm, which was a 1.1 inch storm. You can see we had most of this rainfall occurring within an hour shortly after midnight. And you can see in the bottom image there how stage in front of our barrier inlet window picks up quite a bit until we exceed that ponding extent failure threshold. So the day after this, we went out into the field. This is one of the proprietary screens shown here in a sag condition. So in that low point, kind of receiving water from both sides. And this was debris that had accumulated over a period of 46 days. And so you can see here in some of these close-up images, we've got all sorts of material. We've got organics, cardboard, aluminum cans, and it's effectively blocked all of the inlet, the windows in this particular screen. So the research team went out, we collected this debris, kind of reset conditions, and brought back what was effectively 4.5 gallon-sized Ziploc bags to our lab for analysis. In total, we had 13 of these debris failure threshold events over the course of the 2-year study, which amounted to 271 pounds of material. I will point out that all 13 of these events occurred in Columbus, which is ODOT District 6. We think this happened for a couple of reasons. First, this was the site that had the highest AADT. So I think it was over 130,000 vehicles So quite a bit of traffic load moving across these sites. And the second reason is that these sites were also on some of the flattest topographies. So both longitudinally and from a cross slope perspective, very low slopes. So we think these two reasons really contributed to why we had these debris collection events only occur in Columbus. In support of the study that Troy showed previously, the majority of the debris that we found was small sediment. We also saw rock and gravel as a second most portion, followed by plastics and vegetation. In total, the average failure frequency was just over 91 days. But as I mentioned, these 13 events only occurred in Columbus, or ODOT District 6. Considering the other cities that we monitored in, we did not have any debris collection events. So if implemented across the state, we think that this number could be quite a bit longer. Some conclusions from the field monitoring portion of the study. So as Troy mentioned, we tended to see this smaller sediment trapped in front of the manufactured screens, especially when compared to our proprietary screens. You can see that in the image here on the left. We've got a lot of small sediment, small material that's trapped in front of this particular proprietary screen. Whereas on the right, in front of our fabricated screen, you don't see a lot of that small material, and instead you're seeing larger pieces of cardboard and plastic and that type of material. This smaller sediment is probably acceptable to enter the storm sewer because we think that it poses a low risk of clogging of those sewer pipes. Next, we also, as supported by the laboratory study, found that locations in sag conditions required much more frequent maintenance. So you can see that in the bar plots here. On average, sag conditions needed to be maintained around just over 60 days versus screens in a non-sag conditions, which were over 120 days. We saw similar differences between fabricated screens versus the manufactured screens in terms of their maintenance intervals. On average, the manufactured screens needed to be maintained just under 80 days, whereas our fabricated screens were over 120 days, regardless of whether they were implemented in sag condition or not. So in general, we think that because those fabricated screens that we made were able to convey a lot of those smaller sediment particles, their clogging and maintenance intervals were quite a bit longer compared to the manufactured screens. In April of 2024, we did some field maintenance testing of the barrier inlet screens to ensure that if implemented across the state, these screens could be maintained effectively to kind of reset the hydraulic efficiencies when debris had accumulated to a certain point. In consultation with the TAC as well as maintenance crews across the state, we came up with 3 maintenance measures that we wanted to test. So this included an air compressor, a pressure washer, and then the use of hand tools, all of which were going to be combined with the use of a regenerative air street sweeper, which sort of represented current maintenance protocols across the state. We compared those methods against the regenerative air street sweeper only, which served as an experimental control for the maintenance testing. I want to go ahead and show some images of these maintenance tests in action. So on the image on the left there, you can see quite a bit of debris. This is kind of our initial conditions. So quite a bit of debris had accumulated in front of this screen. I will mention that these particular inlets in District 8 had not received any maintenance for quite a bit of time due to construction that was occurring. So these images will represent kind of the extreme amount of debris that may be trapped in front of the barrier inlet screens. The image on the right there, you can see a street sweeper mounted pressure washer in action, sort of clearing debris from the screen itself and then loosening debris and material that kind of compacts in front of the screen. Once the pressure washing had been completed, we took the regenerative air street sweeper, passed it over the inlet, and you can see on the image on the right there that we've essentially got a completely clear screen, indicating that maintenance was highly effective in restoring the hydraulic capacity and function of this particular screen. Next, as I mentioned, we tested an air compressor. So the image on the top left there, you can see our initial conditions. Again, we've got quite a bit of material accumulated in front of this fabricated screen. On the video on the right there, you can see how that air compressor is doing a great job of loosening up the material, both that had become trapped on and in front of the inlet screen. And then finally, we again took the street sweeper, passed over the screen, and you can see the stark difference between the condition of the screen prior to maintenance and after maintenance had been completed. Again, very, very effective in terms of loosening that material. The next method that we tested was hand tools. So this represented one of our more simple method in terms of the type and complexity of the equipment needed, but it also had some drawbacks in that it required more staff, more kind of hands-on approach to loosen this material. But again, just like the other methods that we tested, this method was also highly effective, and we found loosening that material prior to the street sweeper passing by the barrier inlet screen was a really potent combination to remove the debris from the roadside. The last method that I'll mention here is the street sweeper only. So you can see here the image on the left representing the initial conditions. We found that without that additional maintenance measure to loosen some of this material in front of the screen, the debris was effectively kind of just compacted in place, as you can see here on the image on the right. And we didn't really see a lot of actual removal happening from the street sweeper alone. So what we concluded is that these additional maintenance measures combined with the street sweeper were highly effective. You can see here on the image, on the video on the right, the street sweeper going by after we had used the pressure washer in this case. After consulting with the research team and members of the TAC, we found that the air compressor is likely the most feasible option for barrier inlet screen maintenance at scale. We were really happy in that all of the screens held up well to impacts from the street sweeper, as you can see here with one of our fabricated screens. And we think there might be opportunities for purpose-built systems, something like a air compressor mounted to the bumper of a street sweeper, for example, which could reduce setup time and then personnel and equipment demands. And then lastly, more frequent maintenance in front of these barrier inlet screens may be helpful to mitigate the sort of extreme amounts of debris that you can see here kind of in front of the street sweeper. I will pass this back to Justin to wrap things up.
All right, thank you, Andrew. All right, so based on the findings, from the laboratory, the field investigation, the maintenance demonstrations, we conducted some cost-benefit analysis. We wanted to look at what the cost of these screens is, both the manufacturing, installation, maintenance, compared to the current alternative, which is the debris gets swept into the inlet and then it has to be vacuumed out by heavy sewer and inlet cleaning with a vacuum truck. So this requires, breaking down a whole lane and potentially spending up to a day cleaning out a short series of inlets. Very labor intensive and a lot of time and effort, not to mention it puts ODOT personnel, out there on the side of the road for an extended amount of time. And so what we found is compared to that practice, the vacuum heavy sewer cleaning, the screens are extremely cost beneficial, especially the fabricated screens. They are cheaper to produce, they're faster to install, and they have a universal fit. That was, I think, one of the bigger challenges with the manufactured proprietary screens is that they required detailed measurements of all the inlets before you could fabricate them and install them. So having a kind of a bolt-on ready-to-go option that ODOT can stockpile and have it on hand, we found to be a good benefit there. But as you can see here, this graph comparing basically the sewer cleaning frequency. So how often would you have to vacuum out the inlet after it clogs? And that's what you see on the x-axis there. So if you have to do that every 6 months or every year, your return on investment of installing one of these screens is very high. And we found that even even going out to that 8-year mark, the fabricated screens are you're still breaking even. So even if you only need to vacuum out that inlet once every 8 years currently, you're still better off installing one of these screens, and it's much cheaper to do the sweeping, even with the couple extra seconds it takes to clean off the screen with a power washer or air compressor. It's much more cost effective to treat the debris at the surface than vacuuming it out once it's entered the inlet and entered the sewer. We also looked at the hydraulic results measured in the University of Iowa's laboratory and compared it to ODOT's CDSS calculations. CDSS is ODOT's kind of standard design software they use for inlet spacing and spread calculations. And what we found is that CDSS has a pretty substantial factor of safety built into it. So when we replicated the same laboratory scenario that we were testing with CDSS, we found that even with screens installed, the hydraulic efficiency of the inlet is higher than what CDSS would return for that same hydraulic scenario, longitudinal slope, contributing drainage area, etc. So what this is telling us is that it's a good thing that they have the extra factor of safety. So if we were to retrofit existing inlet sites with these barrier screens, there really is no adverse hydraulic impact. We're not going to worsen the condition, cause roadway flooding, because the CDSS software is already kind of has that factor of safety built in, that there would still be plenty of capacity and the spread would be allowable. Now, I'll bring a note that previous graph was with the grate open. When you have the catch basin grate blinded or closed, you still have a very conservative CDSS value compared to the baseline, but once you get up to those steeper longitudinal slopes, some of that factor of safety starts to fall off. And so we led us to, we released the value in the catch basin grate being present. Whether or not you have a barrier inlet screen installed or not, that the grate is very important. But the higher longitudinal slopes, we did see the efficiency start to drop off when some screens were installed. So overall, the research team did recommend that these barrier inlet screens could be installed starting with areas of known debris issues. And then ODOT can maintain a database and a maintenance log to help monitor these screens for a longer duration, and essentially the rollout could be expanded once all the maintenance SOPs and the maintenance staff get more familiar with the screens, how to maintain them. These screens could be very effective to be rolled out on a statewide implementation. We found that the additional maintenance requirements were not excessively burdensome. Maybe take a few extra seconds to clean them while you're doing your routine street sweeping, but it seemed very plausible and very effective. We also recommended that visual markings be placed on the barrier walls at locations where the barrier inlet screens are installed. This will make it easier for maintenance crews to identify them in the field and know they're there. Also very helpful for snow plows and other maintenance vehicles, contractors, to know where they are and just kind of be aware that they are there during their day-to-day operations. So we do advise to only use the screens when a catch basin grate is present in a sag condition. We notice that sag condition is the most prone to clogging and the most prone to excessive spread and ponding. So really that recommendation applies to whether you're using a barrier inlet screen or not. Just in general, the sag conditions benefit greatly from having that catch basin in place. But we think that in a sag, if you want to use one of these barrier inlet screens, the catch basin is highly advisable. And then some expected benefits from this implementation: we anticipate reduced cleaning and maintenance time and cost to ODOT, safer working conditions for ODOT maintenance personnel, sustained inlet hydraulic capacity, and cleaner receiving waterways. So based on all these findings, the maintenance, the laboratory tests, field observations, we kind of refined our fabricated screen alternatives and came up with what we think is a very optimal design. We looked at the opening size area, so how big is each opening, and we compared that to hydraulic efficiency as well as debris capture ratio. And then looking at those two numbers, we were able to kind of hone in on this optimal opening size. And then we also made a couple other tweaks, such as additional mounting points, and we found that making the screens a little taller allows for more variability in inlet geometry, so they can be installed on the vast majority of all inlets across the state. And then the extra mounting points provide a little extra stability and a little more rigidity to the installation as well. So that was our final recommendation to ODOT. We now have about 10 minutes for any questions from the audience, and then We'll also be publishing our final report in June, so just in a couple days here. And all the details and data will be available at that time as well for everyone's review. And yeah, happy to take any questions at this time.
Thank you, Justin, Troy, and Andrew for that insightful presentation. So if you have questions, please feel free to enter them into the question section on your panel, and I will relay them to our panelists, and then I will give you the answers that they will give you answers to the questions. And our first question is, are the grades easy to remove to allow access to the storm sewer?
I would say that in the scenarios where there is a catch basin grate at the barrier inlet, it's your typical catch basin grate. So I mean, it's heavy, you know. I don't know, Andrew, you've probably lifted a couple of those, 80 pounds, 100 pounds. It's a heavy cast iron grate. But that would be, you know, how you would lift it off the catch basin grate to vacuum out the inlet. One of the challenges though with ODOT is that some of the inlets that don't have that catch basin grate, there is even less access. So a lot of times on those inlets, barrier inlets, they have a maintenance window. It's like a steel plate on the barrier wall itself that has to be taken off, and then again you can get your vacuum hose in there. But it still makes for a very challenging geometry to vacuum out the inlet, especially when you're so close to a live traffic roadway.
I will also add to that the in terms of the screens themselves, it tended to depend on design, but many of them were able to be installed using TAPCon screws, which were relatively quick. Especially our fabricated alternative screens were installed using just 4 TAPCon screws, so we were able to install and uninstall those in under 2 or 3 minutes with a team of 2. I think in the long run, using something a little bit more robust, something like a masonry housing or other types of screws to allow the screens to be installed and uninstalled a little bit more securely would be something to consider at scale. But yeah, certainly the screens themselves don't do anything to impinge on the grates being removed. And if the screens need to be removed, they're often pretty easily done using just a handheld drill and a hex head.
Yes, thank you. I interpreted the question as the catch basin grate, but thanks for the clarification that the barrier inlet screen is also easily removed on and off.
Thank you so much for that answer. We have another question. How long did it take to build the model?
Yeah, good question. We built the model, well, we started with designing it first. And so coming up with the dimensions, the length, the flow conditioning, the head box, and then we had to create drawings for our shop to fabricate everything and get that in place. So once we started construction, I want to say it probably took us around 8 to 10 weeks to fabricate the 90% of it. And then from there, it was commissioning the model, setting up the point gauges, iteratively going through and roughening the deck surface to get the Manning's end correct. That took another 3 or 4 weeks easily to get everything set up and commissioned before we were ready to start doing the testing.
Wonderful, thank you, Troy. We have another question. Can you describe the construction of the fabricated screens?
Yeah, so I think maybe Andrew, if you want to maybe take that one. We designed them, in an AutoCAD software, and then they were manufactured via like a CNC machine at University of Iowa and OSU individually. So the same kind of CAD file went to both groups. But Andrew, a few more specifics about it.
Yeah, so at Ohio State in our department, we're very fortunate to have a welding program and have access to the plasma table. So that was able to be constructed. Those screens were able to be knocked out. I think all 21 of them, or sorry, all 9 of the fabricated screens that we tested were able to be knocked out in a day's work. So that was able to be done pretty efficiently, just using a plasma table that we had in our department.
And those were fabricated out of
Plate, yeah.
3/8 inch or quarter-inch plate steel.
Yeah, also a CNC water jet can be used. Yeah, so they were fabricated out of plate steel. In our case, we used a CNC water jet to cut the shapes. There's a couple different ways they could be fabricated.
Sounds great. Thank you. Our next question, can you review the cost to clean a SAG-CB under the baseline condition compared to the recommendation? Does the recommendation suggest a higher frequency of street cleaning was ultimately cheaper than the original back truck cleaning?
Yeah, so definitely the full cost benefit analysis will be included in the report. So I don't know if I can have time to go into all the details, but we looked at the typical cost to ODOT to perform routine street sweeping based on the personnel, maintenance, vehicles, traffic control, and essentially came up with number of miles that get swept in a day for a routine sweeping operation. And the numbers are something like, for the same cost it takes to vacuum out, the same cost it takes to spend a day vacuuming out an inlet, you can sweep about 40 miles of ODOT roadway. So, that's kind of where those costs come from. We don't necessarily see that there's an increased number of maintenance intervals required at the SAG. We think that the standard ODOT street sweeping frequency, which we found in Columbus to be about once a month, is sufficient maintenance for SAG and non-SAG conditions along these stretches of roadway.
Wonderful, thank you, Justin. Okay, does anyone, we don't have any more questions as of right now. Does anyone have any other questions they would like to get in before we wrap up for the day? Oh, here we go. Another question. What were the debris accumulation rules that OSU developed to notify staff to visit the site and remove the debris?
Yeah, thank you for that question. So in all instances, we established this threshold for what we considered a failure event when ponding encroached within 1 foot of the travel lane. So we relayed that with measurements from our ultrasonic depth sensors, plus the known cross slopes and longitudinal slopes of the roadway to essentially figure out what ponding depth in front of the screen that extent of ponding corresponded to. We also wanted to be sure that we weren't getting false readings from our ultrasonic depth sensors by like a large piece of debris, for example. So we implemented a rule where that ponding needed to pass beyond that threshold for a period of 10 minutes before we considered it an actual failure. When that happened, members from Ohio State went out and collected that debris the next day to reset conditions.
Great, thank you, Andrew. And we have one last question. Will this presentation be shared with attendees or added to ODOT's website? Oh, that's a question for me. Yes, it will be. I will email this presentation out within the next 24 to 48 hours. So thank you for your question. Let's see here. So it looks like that's all the time we have for questions today. On behalf of LTAP and ODOT, I'd like to thank Justin, Troy, and Andrew for once again sharing their valuable knowledge and expertise with us. As mentioned earlier, the recording of this webinar will be shared with all our registered attendees. Thank you all for attending, and we hope you found this webinar informative and engaging. Have a wonderful rest of your day.